One of the most, by and large, observable physicists, Michio Kaku, has discussed his evaluation concerning this issue. Kaku, known for his surprising contributions to the fields of physics, has recently recognized that the James Webb Space Telescope has discovered 6 tremendous, infinite frameworks that experts once thought could not exist. These discoveries have the potential to open up new perspectives in our understanding of the universe. It is, therefore, both fascinating and worth watching these developments unfold. Kaku is a remarkable figure in the scientific field. A physicist of American and Japanese heritage, he is regarded as an expert in both conventional experimental physics and quantum mechanics. Unlike some more conservative and skeptical researchers, Kaku does not belong to that group and has been open to the astonishing recent discoveries of the James Webb Space Telescope JWST mission. We are fortunate that this distinguished analyst has chosen to end his silence and speak openly about what can no longer be denied. The excitement and almost all-encompassing tone of the famous physicist are apparent in his comments on the discoveries made by the James Webb Space Telescope. He proposes that these findings have been the catalyst that has stimulated his interest. We should investigate the ramifications of Michio Kaku's revelation of these 6 immense cosmic frameworks. Kaku is a researcher who has continuously considered new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku realizes that the discoveries of the new telescope might significantly advance the scientific field, even though many of his peers have struggled to embrace this view. This has caused concern and anxiety among both defenders and critics of quantum mechanics. However, this genuine understanding brings amusement to Kaku. The JWST has revealed the discovery of 6 gigantic universes tracing back to the earliest stages of the universe. Each of these vast frameworks contains more stars than our own galaxy, despite forming just a short time after the Big Bang. The group of astronomers who made the discovery has named these surprising frameworks universe breakers, as their existence would change our entire understanding of the universe. Something here no longer aligns with the theory of the Big Bang. The Big Bang theory posits that the universe was a chaotic place following its inception. The first solid objects took several hundred million years to form, and it required countless additional years for these objects to reach sufficient density to produce light. The development of complex structures, such as galaxies, was expected to occur much later. Some of the newfound frameworks exceed the size of the Milky Way, and their enormous brightness suggests that they were likely forming many new stars each year. In contrast, our own galaxy forms stars only sporadically. It remains unclear exactly when the first universes formed, as researchers have been unable to determine this until recently. The one thing that is clear is that, initially, there might have been only single stars or groups of stars that eventually came together to form increasingly larger structures. This process ultimately led to the development of dwarf galaxies, which underwent mergers and grew continuously, as suggested by past hypotheses. According to these theories, highly advanced and massive frameworks could not have existed at that time. This raises the question of whether the universe is simply older than previously thought, or whether complex large-scale structures existed much sooner than expected. This scenario challenges conservative science, which still struggles with this model. Some areas of physics have firmly dismissed this revelation, highlighting potential errors in age calculations. Kaku, aware of these challenges, remarked that there have been many instances of old and misleading theories that endure due to the prominence of certain scientists. Many of these hypotheses were eventually disproven when thorough investigations revealed their inaccuracies. Hence, the vital work in any science, especially in physics, rests with the experimentalists who maintain the validity of research through exact truths. In reality, on Earth, we have limited information about the true origins of the universe. The Big Bang theory was established in 1927 based on observations of the universe's expansion. This information led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to envision a universe with a beginning and an end. The concept of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists face challenges in fully comprehending it. Nevertheless, it is essential to rethink these possibilities. These new insights do not align with what scientists have relied on for years in the Big Bang Theory. However, science has repeatedly shown that reassessment and openness to groundbreaking ideas are key components of the scientific process, just as much as the affirmation of specific theories and observations. When Einstein was young, it was believed that stars and planets were fixed in the universe, and these arrangements occupied a defined space. Now, we understand that everything in the universe is in motion. Planets orbit stars. Stars move within their galaxies at different rates, and entire galaxies move rapidly through space. The ultimate fate of the universe remains unpredictable. Researchers are challenged to accept uncomfortable insights, and it is understood that hypotheses are not definitive until they are thoroughly tested and confirmed by concrete observations. The idea of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Additional evidence, such as cosmic microwave background radiation and the redshift of light from distant galaxies, as well as other galactic patterns, appears to support this theory. However, it is important to remember that people once believed the Earth was flat and that the sun revolved around us. They held similar types of evidence for their beliefs until technological advancements provided a clearer and more accurate picture. We are witnessing a similar situation today. Researchers expected the JWST to confirm their suspicions about the Big Bang, but instead, it has discovered 6 frameworks that appear too large for their age. This reminds us that science is always evolving, and experts must remain open to new discoveries and rethink existing theories based on available evidence. Researchers use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, imagine watching a vehicle coming toward you. As it approaches, the engine sounds louder. Once the vehicle passes you or moves away, the sound changes. This is because the sound waves shift as the vehicle moves. The same principle applies to light. When a light source, such as a distant star, moves toward us, the light we see shifts toward the blue end of the spectrum. Conversely, when the light source moves away, it shifts toward redder hues. This is known as redshift. Physicists convert redshift values into speeds and distances to estimate cosmic measurements. However, it is crucial to note that small errors in these calculations can have tremendous implications. The measurement methods used in the past are now under review, and the results regarding the latest revelations about our universe are exciting. It is important to consider whether these results are genuinely based on redshift errors, or whether some scientists are simply denying the facts. This question requires serious assessment and careful review of the data and methods used in the investigation. As scientific inquiry progresses, discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The discovery of 6 enormous galaxies dating back to the universe's infancy is one such example. These galaxies defy the regular speculation of galaxy formation and raise significant questions about the timeline and processes involved in developing large-scale structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with cutting-edge technology that allows it to peer deeper into space with stunning clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient, gigantic galaxies challenges existing models that predicted such massive structures would have formed much later in the universe's history. The implications of these revelations extend beyond astrophysics and into fundamental physics, compelling scientists to reconsider established theories about the early universe. These findings also underscore the importance of remaining open to revolutionary ideas and changing our understanding based on experimental evidence. Kaku has emphasized the critical role of scientific proof in shaping our perception of the universe, pointing out that theories must continually evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are defenders who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic evolution than previously thought. This viewpoint challenges the conventional belief that galaxies develop slowly over billions of years through mergers and gradual evolution. On the other hand, skeptics caution against hastily discarding established models based on limited observational data. They advocate for a more cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain these unexpected discoveries.